Hi, this is Bernard Brault. I'm doing a follow-up video on a previous video I did on ocean rise, so I'm inviting you to look at the first one where I downloaded some data from University of Colorado, and it's satellite data about sea level. And what I'm interested in is looking at whether or not sea level rise is accelerating or it's not. In the previous video, I used a moving average filter to filter out noise, and somehow I used that because it was nice and easy, and somehow I want to use maybe a slightly different approach here, and I'm going to use a linear first order filter, which is more conventional for signal processing. So let me quickly describe the first order filter I'm going to be using. So a low-pass filter basically filters out high-frequency noise. And why do I want to filter out high-frequency noise is mostly because what I'm interested in the data is not so much the ocean level, it's the rate of increase of the low ocean level. Actually, it's more than the rate of increase. The rate of increase is velocity, right? And then the rate of increase of velocity is acceleration. So in order to go from the input, the data that I have, to acceleration, I have to differentiate or do two derivatives. It turns out that a derivative is an amplifier for high frequency noise. So if there's any noise in the high frequency region, it's going to get amplified. So you need to remove this noise by filtering it out. And one of the nice thing about this first order low pass filter is that it does exactly this, and it does it in a way that completely compensates for the derivative high pass filter. So in the low frequency range or low frequency region, it does not affect the signal, but it does so in the high frequency range in a way that does not impact the derivative. So the low-pass filter takes a time series x of t, which is in this case height, eventually velocity and acceleration, and gives me an output. And the way to describe this filter would be to use first-order differential equations. But using derivatives, solving derivatives, and all that, it's a little complicated compared to other techniques. So we came up with a really nice trick is to transform the input variable into from the time domain to basically some form of frequency domain, similar to I would say a Fourier transform, except instead of having only a frequency component, it has a real and a frequency component. It has like a not just a frequency, but frequency plus amplitude. So that's the Laplace transform. And Laplace transform does two really neat tricks for us. One is that it turns differential equations into polynomials. That's the first thing. And polynomials, I mean, that's what you learn in high school. You can multiply them, you can solve them, and so on. Versus differential equations could be a little trickier. The second thing is that in the time domain, a filter, in order to get the output of a filter, you need to do what's called a convolution, which is like a lot of mathematical operations. And in the frequency domain or in the Laplace domain, that convolution turns into a multiplication. So today with computers, it's a lot easier to work in the time domain, but the mathematical tools of looking at this in the Laplace domain, if you want, or in the S domain, makes things a lot simpler, and that's why we prefer to operate there. So the filter that I'm describing here as a transfer function, we call this a transfer function, is it takes this x of s input, transforms it into a y of s, and the transfer function is 1 over tau s plus 1. It's the simplest filter, right, that you could find out there in its category. It's a first order filter, and it has the following characteristic. you could look at it, from the time domain or the frequency domain. But let's look at it in the frequency domain. So a little bit similar to if you want to filter out high-pitched noise, let's say for a sound system, like a speakers and sound system, you have a hiss, and it turns out to be a high-frequency hiss, and you want to filter it out. So you have a low-pass filter, so everything in the low frequencies get across, and the high-frequency noise. And remember, I told you that when I'm going to measure velocity and acceleration, I'm going to get a lot of that noise. You could exactly cancel it out with this kind of filter. So that's what it's showing here. So what you have is a 0 dB gain up to a certain frequency, right? So 0 dB being a unitary gain. That means no gain, no amplification. So you're getting the same signal in the low frequency range. And once you reach a certain frequency, which is the frequency is the angular frequency, is the reverse of this 1 over tau, this constant right here, it starts to attenuate the higher pitch. And the higher the frequency, the more the attenuation. Now, when you look at it from on the time domain, right, one of the ways to look at it is to look at the step response. So imagine this X here is this blue line. It goes from 0 to 1 suddenly. Goes from 0 to 1 and then it stays at 1. It's impossible to do in real life, but let's assume that you could do this instantaneously, go from 0 to 1 and stay at 1. Then the output of this filter would look like this orange line right there, right? So it would actually filter out this sudden step and just gradually, smoothly, basically grow into this, so make this step something a little smoother. So filtering out, again, the high frequency. And it does this without overshooting. It does this sort of nicely, and I think it's going to be a nice filter to use for this case here. Back in the filter, so just to show you a little bit about the filter, here's the input of the filter in blue. And I'm showing this as the X column right there. So going from 0 suddenly to 1 and staying at 1. And here's the output Y, which is in orange right there. And here's tau. And tau is the configurable parameter. And it's going to be a fixed parameter. I could make it a variable parameter. We're not going to do this. It's not going to be an adaptive system or anything like that. It's just very simple. If I change tau, let's say from 2 to 5, you'll see the effect on the filter, right? So you see I changed from 2 to 5, and all of a sudden you see that the filter here, the filtered is more filtered, right? So it just responds more slowly to this sudden step. If I make the 5 to 10, right, then it's going to be even smoother. Actually, 10 and tau is called it's measured in seconds or in time, and it's the time it takes for the filter to actually grow to 62% of the value. So being at 10 right here, you see it grows to 62. So if I change the 10 here to 20, it's going to take 20 seconds to get to 60 some percent. So 20 seconds more or less here, 60%. And you see now it's like but it's not following the input very well. You see it's filtering out, but I'm sort of losing a little bit of the input signal. So if I go back to tau equals to, let's say, 3, so it's going to be a little sharper right there. But it won't filter out the high frequency noise as much as the previous one would. All right. So, and I can show you the frequency response, but I don't want to run out of time what I'm trying to do here, but it's more or less the same thing. So I have an input here, which is a sine wave there, and let's say this is the noise that I have and I want to reduce it. So as you can see here, using a tau of 20, it reduces the noise, and the signal the output of this filter is this reduced sine wave. It has one side effect, is that it creates a 90-degree lag. So you notice that the peak here is, or the peak of the filtered signal corresponds more or less to the 90-degree offset or lag of the input signal. So let me just change this to 10, let's say, and you see. So now you see the signal is not as filtered, it's a little higher. So if I change it to, let's say, 3, so notice that as I'm changing the tau value, I'm changing how much filtering I'm applying on this, on these frequencies. All right, so let's go back to sea level rise. Okay, so I'm back to sea level rise, and this time around, I'm inviting you to look at the previous video, but you have ocean height, and that's the data in green here that I downloaded from the Colorado website. So this is the raw data. That's all these dots that you see is the raw data. The red line that you have there is given to me by Excel. Now, you don't have to make any effort. You can be lazy if you want and just draw this line, but it's not going to do all that much more for you, right? And you see more or less that ocean rise is 3 millimeter per year, and that's what you see here in the red line. But what I'm interested in is looking at acceleration. So in order to look at acceleration, I need to derive this twice, and I also want to do some filtering. So one of the first thing that I did is I'm going to plot the sea level rise, the same plot here, except I'm going to remove some of the high frequency noise, and that's what I did with this time series right there. So what you have here, H, this here is this plot right there in blue. Right, so it's the same little dots there, but they're slightly filtered out, and you see the tau y there. This is the tau value from the filter. If I change the 0.3, let's say, to 5, what you'll see is that the signal is completely filtered out, but you see here I'm losing more or less, like, you know, the granularity. I'm basically not getting a signal anymore. But if I make tau 0.01, then it becomes, whoops, what happened there? Tau 0.1. There you go. If I make 0.05, I should say, maybe, I don't know what happened there. So it's getting more noisy, right? So if I make tau a little too small or too large, it just gets too noisy. So we're going to go back to something like 0.3, right? Or even actually 0.1 kind of works even. 0.2, let's say. Well, let's use 0.2. Yeah, it's kind of nice. So you're filtering out the noise, but you're still getting more or less a fairly nice signal, right? So this is height filtered, so that's the same data there. And of course, if I draw a plot, if I plot a line, again using the lazy Excel formula, then I get the same trend line. So moving to the next couple of things. So I want to get velocity, right? So I explained this before, so I'm taking the derivative of this, all right? So I'll skip on how I did this, but the next step here is the velocity here, and that's the data that you see here right there. But you see the velocity, because I'm taking the derivative, look, the data is all over the place because I'm getting all this high frequency noise. So I'm going to filter out the noise, and filtering out the noise is giving me this filtered velocity right there, and I'm using again another low pass filter to do this. This time I'm using a tau of 0.6, right? And it's giving me this plot right there. So this is basically ocean rise speed, how fast the oceans are rising. And as you notice, they're not rising constantly at 3 millimeter per year. Sometimes they're going a little faster, and actually sometimes they're actually decreasing in speed. But see, on average it's about 3 millimeter, and that would be 3 right there. This is the average. So some years is going faster, some years are going slower. So what I want to get to now is the acceleration. So again, I'm taking this velocity, I'm doing another derivative on which is going to give me the unfiltered acceleration. That's going to pick up a whole bunch of noise again, and that's the noisy acceleration. But notice, even though it's noisy, look, it's clustered, right? It's clustered around the 0, right? So notice that all these data points, unfiltered data points, where are they? They look like they're averaging around 0, but let's filter them out. This is the last filtering using a tau on acceleration of 1. And I'm getting the final result here, which is ocean rise acceleration. And if I plot a trend line across the ocean rise acceleration, what do I get? I get 0 trend, right? So there's as many data points under 0 decelerating as there are accelerating, all right?